Hi everyone, this is lecture 8 of MA 221 and we will be discussing today about improper integration. Okay, um, so as we are discussing that integration basically is if you have a function f, say, which looks like this, and you have 2 points a and b, then integration of fx from a to b, which is a to b fx dx, is basically the area of this um, shaded region. And your job is to find a function f such that f prime x is small fx, and then you'll get just fp minus fa as your answer. Now the question is, um, if you have one integration like this, okay, integration minus 1 to 1 over x squared dx, then your natural instinct should say that why not I do like this, x to the minus 2 dx. And then we know that this is basically minus x to the minus 1 and the limits are minus 1 to 1. So if you put the values in, you'll get minus 1 over 1 and then just minus of minus 1 over minus 1. Okay, probably one more step would be like better. This is minus 1 over x from this. So I have minus outside and then 1 over 1 minus 1 over 1. So basically I have 1 plus 1 and 1 minus 1 the beginning. So this is just minus 2. Okay, cool. But then again, if you try to see the graph of this function 1 over x squared, it kind of looks like this. So this is minus 1, this is 1. So basically you are trying to find the area of this region, right? And by default, you can just guess that it should not be negative 2, right? Because this is like this should give you some positive quantity, the area of this shaded region, okay? So there is something wrong going on. And maybe one other students kind of deals this like this. Maybe he just split the integration from minus 1 to 0 and 0 to 1, right? So he's basically considering this subinterval and then from 0 to 1, the other subinterval. And you have 1 over x squared dx, just like before. Then if you calculate this, say I want to work with this part separately, say, and work with, oh, rather, same thing, but yeah, say, and work with this part, then 0 to 1, 1 over x squared dx is there. So if I consider the graph, so 0 to 1. So I'm interested in this this region, area of this region. And remember, this graph is like continue to grow towards y to be positive infinity. So as near 0, the function kind of increases very rapidly. What I can do is I can assume this to be t to 1, limit t tends to 0 plus, and then x to the minus 2 dt, right? So this will be basically minus 1 over t, and then limit t tends to 0 plus. The 0 plus means we are approaching from this side, from the right side towards 0, right? Because we know that at 0, the function kind of increases rapidly. So therefore, we just consider this t here maybe, and then we would push this t to be 0 using limits. This is kind of a standard idea in many areas of mathematics. And this will be just limit minus limit t tends to 0 plus 1 over t minus 1. And from like basic calculus, you can say that this is plus infinity, because 1 over 0 is like very big. So yeah, so therefore the other student can say that this integration diverges, right? And so in the second process, you could not find anything wrong, right? It seems like reasonable. So the thing is, when okay, so let's look about what is an improper integration first. Then we'll see that what actually is going wrong with this idea. So the improper integration is a definite integration most of the time, in which either the function being integrated has a vertical asymptotes on the interval of integration. So if I try to draw a picture, then say I have a function like, I don't know, like this. Yeah. This is 0, so this is 2. So therefore, I can call that this line, which is just x equal to 0, is a vertical asymptote. Why? Because informally speaking, as you go near to 0, the function kind of approaches towards this line and kind of behaves like the line when you go very high towards infinity. Okay, cool. One such example might be minus 2 to 3 dx over x minus 3, right? Why? Because I have, what is my interval of integration? This is like, in this case, this is 0, 0, 1, this is 2, minus 1, minus 2, minus 3. So basically, this is my interval of concern right now, depending upon the lower and upper limits. Okay. Okay, my screen freezes somehow. Okay, sorry, my screen got frozen. So yeah, so I was saying that my interval of integration is from minus 3 to 2 in this case, and oh, it should go from here to there. Minus 2 to 3. Then at 3, when I put 3 in this integrand, then I'll get 1 over 0, right? So therefore, at 3, I have a vertical asymptote. I hope things are making sense. One more example could have been like minus 1 to 2 dx over x squared. So I know that my interval of integration is now minus 1 to 2, and there is 0 in between, obviously. And at 0, I get 1 over 0 square, which is like infinity. So therefore, this is also a vertical asymptote. At 0, this function has a vertical asymptote. Okay, and so on. The one good question might be, is this integration improper? Let's see what's the interval of integration -2. So rather, one more approach can be like this. When 1 over x plus 3 is infinity, if the denominator is 0, right? That means x should be -3. But -3 is not in the interval of integration. The integration goes from -2 to +2. So therefore, though this function has a vertical asymptotes, but we're not bothered about that because my interval of integration doesn't contain the vertical asymptotes. The function will look kind of like this. Right? It should go from -2 to 2, which is perfectly fine. This area can be easily calculated. Okay. So this is first type where you have vertical asymptotes. And for second type, if you see in the integration, either one of the limits of integration having like containing plus or minus infinity. So for example, like a to infinity fx dx, or like say -2 to, or rather minus infinity to 1 over x dx, something like this, or like minus infinity to infinity 1 over x plus 2 dx, something like this. Okay, now let's look at some examples and how to deal with both of the type of integrations. So type 1 is where you have asymptotes, particularly vertical asymptotes. So say um, okay, just a second. Okay. So it says that if the asymptote is at an endpoint, so vertical asymptotes can be like two types. If you see that the vertical asymptote is at one endpoint, for example, say a to b fx dx, okay, and say fx kind of looks like this, and this is your point A, this is your B. So I can see that at A, I have a vertical asymptotes, right? So therefore, you should go like this, limit t tends to A plus, because you can't move from the left of A, right? Because that is not in the interval of integration. So you must move from right towards A. So that is the correct way. Hmm. Okay. So you should write limit t tends to A plus and then t to B f of x dx, and then proceed with the integration. On the contrary, if you have something like this, say this is B, this is A, that means you have vertical asymptotes at B, then you should write that integration as limit t tends to B minus and then A to t fx dx. Why t tends to B minus? Because now you can't move from the right towards B, right? Because this is not in the interval of integration. Therefore, you should move from left towards B. Okay. This is one type when you have vertical asymptotes exactly one of the endpoints. And type 2, I mean the other type of vertical asymptote that you might encounter is when the asymptote is not exactly at one endpoint. It might be in between the interval somewhere. For example, say I have something like this, a to b, or rather, yeah, this fx dx, say, and the graph kind of looks like this. This is your A, this is your B, and this is your C. So if the vertical asymptote is at C, where C is like in between A and B, then first you should break the integration like this. From A to C, I'll integrate, and then C to B. Okay. Yeah, and then you just follow the type 1. So where I have problem at C, so therefore T tends to C, say A to T, but C is there, so it doesn't matter if you take plus or minus, because if you approach from right or left towards C, both of the ways are right, because C is now a middle point. So this way is also valid, that way is also valid. I'll just work with C minus, that means approaching from the left. And then you can take limit T tends to C plus, say, and then T to B fx dx. And then kind of evaluate thing. Okay, one important remark I want to make here is, say for example, I just name it. This is I, so this is I1, this is I2. If say I1 is I2 is same as minus infinity, then it makes sense to say I is negative infinity, right? But if, and so is true for positive infinity as well. If both of this I1 and I2 are positive infinity, then some of them will also be positive infinity. That's fine. But if you get that I1 is like positive infinity and I2 is like negative infinity, then you should say that I doesn't exist, right? Because this is a little bit a tricky part of argument though, but I'll say that plus infinity and minus infinity doesn't make it zero. Okay. Yeah, just keep that in mind. Okay, now let's solve some problem. Say first problem is this. Okay, so, and this is a problem of type 1. So it should have a vertical asymptote. So basically I have to look when root x minus 1 is 0. You can just say it directly that x to be 1. So therefore at 1, I have a vertical asymptote. So what I will do is like I'll take limit t tends to 1 plus or minus. So this is my interval, like 1 to 5. So if I go from my minus like left of 1, then it will not be inside the interval of integration. So therefore I should go from right side of 1, which is denoted by 1 plus. So this is t to 5 dx over x minus 1. Okay. Now you take the substitution u to be x minus 1. Then this will be like, so you can use this, no problem. But if you do it at the end, you'll get something like 2 to the x minus 1 half. Okay. And then t to 5. If I write that down, it should be 2 square root 4 minus 2 square root t minus 1, where t tends to 1 plus. And now if I put t equal to 1 there, this is completely fine, right? This quantity is a constant, so no problem. And if I put t equal to 1 in the second part, then I should get just 0. This will be like 0. And that will be just 2 square root 4, which is just 2 times 2, which is just 4. This is your answer. Okay, cool. Not so hard. Second example, I have two problems in that. Say I'll solve A first. Okay, so I have minus 2 to 3 dx over x minus 1. Okay, clearly the function has a vertical asymptote at 1 again, right? And now this time 1 is inside negative 2 and 3. So therefore I should split the integration like this. Minus 2 to 1 and then 1 to 3. Dx over x minus 1 plus dx over x minus 1. Okay, so far so good. Now what I can do is like I can write limit t tends to 1, say plus, doesn't matter. Should be like from on the form like this, dx over x minus 1 plus, again I have to take limit there also. Let's say limit t tends to 1 minus t to 3 dx over x minus 1. I have ln x minus 1 minus 2 to t, limit t tends to 1 plus, say, this limit t tends to 1 minus ln x minus 1. This goes from t to 3, right? And then if I write that down, it should be like ln. Okay, it's very exciting. Okay, cool. So this is just t minus 1. And then if you put negatives 2 there, you should have minus ln 3, right? Modulus is there, so minus 3 will become plus 3, right? And then limit t tends to 1 plus limit t tends to 1 minus, and then you have limit ln 2 minus ln modulus of t. Okay. Now if you put t equal to 1 there, you'll get ln 0, right? And then minus ln 3 plus ln 2 minus ln 1. Okay. So the ln function kind of looks like this. At 1, this is 0. And at 0, this is like negative infinity. So you have negative infinity minus ln 3 plus ln 2. And at 1, the ln function is 0. So this is just negative 0. So in fact, as you have only negative infinity coming into picture, so this is like negative infinity. That's it. So you can say that this is kind of diverges, right? We'll say the improper integration converges when, I mean, you have some finite value there, no infinity. Okay, so this is one question for you to think. Can you answer the question that is this integration 0 to e ln x dx kind of converges or not? As I said, ln kind of looks like this. At 1, this is 0, and at e, the value is 1. Okay. This is kind of asking you the area under the curve, like 0 to e. So therefore, this is asking the area like this. Is the area is like a finite quantity or not? That's the question. Okay. Let us discuss about the type 2 now. So in type 2, you have at least one endpoint with positive infinity or negative infinity. So to deal with that, okay, say first, for example, if you have a to b gx dx, say, then you will write limit, okay, a to infinity, sorry. Limit t tends to infinity, a to t gx dx. Okay, kind of same logic as we have used for vertical asymptotes. And if you have, say, negative infinity to a gx dx, then you will do the same. Limit t tends to negative infinity, t to b gx dx. Okay, so the main issue is that if this limit exists, then we say that the improper integration converges, else we'll say that this is divergent. Okay, cool. Let me go to some examples. Maybe I'll solve A and C. Okay, for A, you have 1 to infinity 1 over x squared dx, right? So what you should do is limit t tends to infinity 1 to t 1 over x squared dx. Okay, and we know that this is minus 1 over x from 1 to t, and you have limit t tends to infinity in front. This is basically minus 1 over t plus 1, right? And we have limit t tends to infinity. So you have minus 1 over infinity plus 1, which is like 0 plus 1, which is it. Sorry, which is 1. Okay. Yeah. So therefore, this is converges. For C, what you need to do is basically you will kind of consider minus infinity to infinity 1 over x squared plus 4 dx, right? So if you have both of the upper and lower limit as like very large quantity, namely positive and negative infinity, you can just split that with any point. I'm doing it to be 0 because most of the time that is like easy to calculate. This splitting is quite fine. You can do it. And then just take limit t tends to minus infinity, t to 0, 1 over x squared plus 4 dx. And you can use just other variables, say L to positive infinity, 0 to L, 1 over x squared plus 4 dx. I've used t and L just to avoid any confusion. Okay, we know that integration of this will be like 1 over 2 arctan x over 2. I have already kind of dealt with this type of integration from 0 to t, limit t tends to negative infinity. And then you have limit L tends to positive infinity, 1 over 2 arctan x over 2. From 0 to L. Okay, there's some mistake. Okay, cool. I get it. It should be from t to 0. For this part, I'll get half arctan 0 over 2, which is 0, minus half arctan negative infinity over 2, which is negative infinity, right? And for that part, second part, I'll get half arctan L, and L is like positive infinity, and then minus half arctan 0, right? And then basically this and this cancels out and gives you minus half arctan negative infinity plus half arctan positive infinity. And if you try to calculate it, then you'll get this quantity arctan negative infinity as negative pi over 2, and arctan of positive infinity is positive pi over 2. So you have pi over 4 plus pi over 4, which is pi over 2, basically. Okay, so this is your answer. And maybe I just take a note that how I get arctan of negative infinity to minus pi by 2. I suppose that arctan of negative infinity is like theta. Okay. Then tan theta should be infinity, minus infinity. And now I'll consider myself thinking that when tan theta is negative infinity, I can easily guess that when I have tan minus pi by 2, which is basically sine minus pi by 2 over cosine minus pi by 2. Sine minus pi by 2 is negative 1, and cosine minus pi by 2 is like 0. And this is basically negative 1 over 0, which is like negative infinity. So therefore, this is true. So theta is minus pi over 2. This is how you just basically guess what will be arctan of negative infinity. Okay. Yeah, I guess this is it for today. I had not solved too many problems, I know, but yeah, you just try to, and I don't think that this is like a very difficult topic to like solve problem, but just follow the, I'll suggest that just follow the basic general uh, rule for each of the types. And if you face any difficulty, then yeah, meet me in today's office hours, or like uh, Monday's office hours in morning. Today, my office hour will be at night. Okay, from 7 to 8. Okay. I can write that down at the very end, maybe. Cool. That's it. Thank you.